All right, here are the announcements that I know of. I will try to get through them as quickly as possible. They have a really bad habit of this, sending out an announcement on Monday morning of something that's happening on Monday morning. So I wish I could have told you about this sooner, but maybe you can still participate. Join the Office of Student Financial Services and our guest, Ms. Penny Sumner, for an observance of Constitution Day today on both campuses. Unfortunately, you can't go to the first one, okay, because that's when we're meeting. Okay, it's 11 o'clock this morning on this campus, and that's down in the faculty staff dining room. If you really feel like you need to attend to it, it'll be okay, but that's this. They have it again at 1 o'clock on the Birmingham campus at the new Student Success Center in the auditorium, which I'm not really sure where it is. I assume it's somewhere on the first floor. Do y'all know that building well enough? But go there and ask, and you'll find out. And you can contact Ms. Williams, Sarah Williams, in Financial Services Office if you're interested. All right, this is a continuation of what we had last time. College Scholars Bowl team is currently recruiting players with knowledge of any subject, including history, literature, science, music, current events, mythology, mathematics. We said mathematics before mythology, but never mind. Okay, but anyway, they are still recruiting people. They had a good turnout last week. Check into it. Okay, let me get this one next because this one's current. The Birmingham Holocaust Education Center has graciously loaned the Darkness into Life Alabama Holocaust Survivors through Photography and Art exhibit to Lawson State Community College Library. The sensitive exhibit of photography through bold and thought-provoking art offers a special glimpse into the private memories of 20 Holocaust survivors living in Alabama. The collection reveals stories of childhood past, stolen family and friends, despair and sadness, cruelty beyond belief, and then stories of bravery, the joy of liberation, and new lives in Alabama. The exhibit will be on display in the Lawson State Community College Library, Birmingham campus, that's the West Campus, from September 4th, which has already been there a while, through the 23rd, which is next week, Monday maybe, or something like that. Okay. Esther Levy, okay, daughter of Toby Komornick Gerson, will speak about her mother's personal experience as a Holocaust survivor. That is today, September 16th, 5:30 this afternoon in the ACAT Technology Theater that's on the Birmingham West Campus, the next to the newest building on campus over there, the one with the slanted green roof in the corner down there, kind of across from the gym. Okay, several exhibition pieces. Oh wait, light refreshments will be served beginning at 5. These are students I'm talking about. I've got to get the refreshments in here. Okay, light refreshments will be served beginning at 5. The program begins at 5:30. Several exhibit pieces will be on display at this event, so you can look at those while you're munching on your munchies between 5 and 5:30, and then afterwards too. And this, by the way, is open to the public. So if you have any friends, family members, anyone else who's interested in that awful bit of history, that's today. So get the word out. All right. Let me do this one next. The Federal Reserve would like to invite you to watch Exploring Careers in Economics, 10:30 Eastern Time. That would be 9:30 our time on October 11th, 2019. You'll hear from and engage with Federal Reserve staff and research assistants. It's organized to broaden awareness in careers in economics and further develop the diverse pool of talent interested in the field. Blah, blah, blah. So if you want to read this announcement, you've got plenty of time to plan for it. That's coming up. That goes along with the College Fed Challenge. If you're interested in that, I have information here, and there's more websites listed here. And here's a flyer for that. This is the last day I'll probably be announcing these, because I'm going to give these to Mr. Armbruster to give to the economics instructor. But the NCAS, that's NASA Community College Aerospace Scholars Program, is going to be accepting applications through October 16th. So less than a month to go. How long do these applications take? Were they pretty hefty applications or not? You remember? Okay, so you probably get it done in a day or two or a few days. Okay, so but don't put it off. Okay, here's that. All right, any questions? Okay, let me. Wow. I was hoping they would have. Okay. They show too much here, but let's deal with it. Find the area of the surface. Oh, any questions before we get started? Anything we've covered so far? Okay. Example 6, top of page 480. This is Chapter 7, Applications of Integration. 7.4 is arc length and surfaces of revolution. We're into the surface of revolution part, the last two examples in the section. Find the area of the surface formed by revolving the graph of f of x equal x cubed on the interval from 0 to 1 about the x-axis as shown in this figure. Okay? Here is the graph of f of x equal x cubed from 0 to 1. Now, as you recall, if you had shown more of this, it would have started down toward negative infinity, come up here, flattened out a little near 0, and then go positive here, and goes up and then heads to positive infinity. We're only interested in this interval from 0 to 1 here. So the part over here doesn't matter, the part beyond 1 doesn't matter. So here we have it, and we have a very narrow megaphone, because we're taking this part and revolving it around the x-axis. Okay. So, our radius of revolution is your f of x, right? That's going to be, that's the radius of revolution is your f of x. And here's Todd. I'm sorry, Devin Todd. Okay. I see your name, your last name first, and then I'll tell you about that. And even Dawson decided to show up today. Did your fellows? Here. Fellow swimmer is here. Josh, there you are. All right. Deal. All right. And Jemiah's here. I think these guys just turned up the clock or something here. Everybody's coming at once here. Okay. Good deal. All right. We've just gotten started on example 6. On page 480, it's Chapter 7, Application of Integration, 7.4, Arc Length and Surfaces of Revolution. We've done the arc length portion. We're on surfaces of revolution, which involves arc length, so we haven't lost it. And these are the last two examples in the section. This is example 6. So I was just saying, here is the curve we're revolving, f of x equal x cubed, only from 0 to 1. X going from 0 to 1. So the other part of the curve that would be down here or continuing up there, we're ignoring. Just the part 0 to 1. And revolving that around the x-axis. Since it's going around the x-axis, your radius of revolution is that f of x. Because there's no offset, anything else that you're having to fiddle with, that's your f of x. So it sounds like to me, looks like to me, it's going to be a really good idea to use dx's here. So let's plan to do a dx, which they shown that then, but so let's do, let me get my pen set up. Well, it won't set up the pen. There we go. So we'll do dx's, okay? So that will be the thickness, well, the dx here, that will relate to the little piece of arc length we have up there. Like I said, surface of revolution depends on arc length as well. So there's your, what you might call your ds, that little increment of arc length here, okay? And even Brian decided to show it today. Good deal. Okay, we're just missing the other Devin and PR. So hopefully they'll be coming in too. We're on example 6, which is on page 480, chapter 7, application of integration, 7.4, arc length and surfaces of revolution. This is the surface of revolution. The function that we're revolving around the x-axis is f of x equal x cubed, only on the interval 0 to 1. So the part that's down here, not messing with. 0 to 1, the part up there, we're not messing with. Just this portion of the cubic function. Okay? And since your radius of revolution, since you're going around the x-axis, the radius of revolution is going to be your f of x. So it sounds like a good idea to let x be your variable of interest. So we'll make a dx there. That dx relates to this part up here, which I call the ds. The book doesn't call it that, but this is your incremental part of your arc length. So that part we're going to be, it's necessary to deal with, okay? Now, if you go back to your arc length, okay, that ds part here that we're going to be dealing with, what is your formula for your arc length? Does anyone recall? Anyone? A long time ago, no less Wednesday, at least 5 days. Anyone remember? Make your guess. Second? Okay, now, yeah, you're giving me the surface of revolution, which we'll do. So then we'll make this a capital S. Okay, so 2 pi is going to be the part of the circumference that this is going to be cutting. You see, this little ds here is cutting all the way around and coming back on the back side and coming around. So its distance of travel will be the circumference. The 2 pi is the first part of that, and the ds is going to be the next part of that. And that's what I was getting at. What in the world is that ds? That's your increment of arc length. How do we do the... oh, I'm sorry. Let's go ahead and put it, since we started with the 2 pi, the radius is going to be your f of x, which is x cubed. Okay? So 2 pi x cubed, that's the circumference that will be cut by this little ds. So the length of that ds is what goes there. So 2 pi radius, f of x is x cubed, times ds. The key here is figuring out what the ds is. Okay? And what is that? Say again? Of what? Yeah, okay. All right. Gotcha. I know what you're talking about now. Yeah, you're going to have to take the derivative of this. Okay? So let's start with that. F prime, that was supposed to be a prime. How it came out a vertical line, I don't know. Okay? F prime, where f is x cubed, what is your f prime? 3x squared. Okay, and what do you do with that? You what? Not yet. Square it first, okay? You want f prime squared, which would be 9x to the 4th. Now you add 1 to it. Okay, and then what? Anybody? Square root of it. Yeah, okay. Square root of that. Now that's what your ds is if you put a dx out here. So instead of ds, that little increment of arc length, that's what you're dealing with, okay? Your f prime squared plus 1, square root of that, times your dx, okay? That gives you this. So what goes here is the square root of 9x to the 4th plus 1 ds. Dx now, because this was my dx. ds. They sound too similar. Okay. Now, and where do we integrate from and to? Now that we're in x's, not s's. 0 to 1. Perfect. All right. Now, how in the world do we do that? How would you approach it? In fact, I don't even think I want to write that down yet. Say again? I heard something, but I couldn't make it out.
Use substitution.
Oh, well, let's do that. Let u equal what? Yeah, the innermost part of the most complicated part of your thing. And that would be the 9x fourth plus 1. Now, the book probably puts that as 1 plus 9x to the 4th. I don't care which way you write it. It's the same, okay? Then what's the next thing you do? Then, help me. Say again? du is equal to, help me? Kind of a big number, but we can handle it. 36x cubed, what? One other little piece you got to have there. You got a d on this side, you got to have a d on this side. dx, perfect. Okay. Now, I look up here and I see we do have an x cubed dx, but we don't have a 36x cubed dx. So what should we do? Divide out the 36. Okay. Now I think we're ready to roll, maybe. The s is equal to, now we got a 2 pi up here on the outside anyway. We're going to bring out our 1 over 36. Well, 2 over 36 is 1 pi over what? 18. Okay, nice round number, okay? And now we'll rewrite this as, by the way, this disappears. There's our x dx, which is 1 over 36, which we pulled on the outside, and that's now leaving our du here. And what else do we have?
Square root of u.
Seconds? Okay, square root of u, but I usually don't like to integrate square roots. U to the 1/2 power, I like that. Now, one other little thing do we need to do? Yes, our limits on the integral, okay? And what were they? When x was equal to 0, what would u be? 1. So it's going from 1 to, and when x is equal to 1, what would u be? 10. Okay, 1 to 10. That's your du here. I mean your limits on u. All right, so this is going to be, I think I can probably do this one, but maybe with some help. Pi over 18. What's the antiderivative of u to the 1/2? Anybody?
2/3 u to the 3 over 2.
Okay, was it u to the 3/2? Is that what you said? Times 2 over 3. Perfect. Divided by 3/2, which is the same as multiplied by 2/3. And we will go that from 1 to 10, which is going to be sort of a pain in the neck, but we can handle it. Now, one thing to note here, we can take this 2/3 outside too, because that's just a constant. This is 2 will go into 18 9 times, and 3 times 9 is 27. So now we have pi 27ths, another nice round number, Okay. Times what? What goes there? Anybody?
The 9x to the 4th
Say that one more time.
plus 1. The 9x to the 4th plus 1. They put that back in now.
Okay. Not necessary, because we changed our limits, remember? So we can just plug in the limits. We don't have to go back to the x's anymore.
Why did we change our limits?
What's that?
Why did we change our limits?
How did we, or why did we? Say again.
10, 1.
How did we get that? Okay. Up here we knew our x's, the dx is going from 0 to 1. And when they did the u substitution, Dawson told me to. It's not my fault, it's his fault. Or somebody told me to do, he told me to use substitution, but someone told me to use 9x fourth plus 1. So when I put a 0 in for x, that gives me a 1 in for u, right? Right? 0 for x, 1 for u. I'll put a 1 in for x, this would be 9 plus 1, so it'll be a 10 for u. So since we made that change, we don't have to go back to this anymore. We can use.
How's our DU 36?
What's that?
How's our DU 36?
How is our du what? Oh, okay. If u was the innermost part of this, right? 9x fourth plus 1, then du is 4 times 9 is 36. Drop this by 1, and derivative of 1 is 0. Okay? So that's where you get this, dx. Okay? Now, we had an x cubed dx up here without a 36, so we divided both sides by 36. So our x cubed dx is equal 1 over 36 du. Well, I want the du in here. I'll bring my 1 over 36 out here, and that becomes a pi over 18. So there were a lot of things going on there.
But we just got rid of the pi over 18.
That's how we got the pi over 18. Okay. Then when we integrated this and got u to the 3/2 times 2/3 over 3/2, the same as times 2/3, then the 2 will go to 18 9 times, and 3 times 9 is 27. So now it becomes a pi over 27. It keeps changing every step. Until now. Until now we got it not. What do we do from this point? We've gotten rid of our 2/3. All we got is u to the 3/2 evaluated from 1 to 10. So what will that be? Second? That is one way to express it. Another way might be 10 root 10. Is that another way to say square root of 1,000? Because 100 times 1,000, square root of 100 is 10 times root 10 minus what? 1. That's about as clean as I can make it. So from this point on, pull out your handy dandy calculators and see what you get here. 10 root 10. Root 10 is something a little bit greater than 3. 10 times that is a little bit greater than 30. Minus 1, that's going to be something probably pretty close to 30. 30 divided by 27 is going to be something a little bit greater than 1. So something a little bit more than pi. I would just guess 3.5. Just a rough guess. And what do you get? 3.563. So not too far off. That's approximately 3.563. Now, was I going through all those approximations and stuff just to waste time? No, when you enter this on the calculator, I think it's a good idea to know about what to expect as an answer. So if you got 35.6, you whoa, that's way too big. Or 0.356, wait, that's not working either. So think through it and see what you're expecting to get, and when you do your calculations, you hopefully are somewhat close. And we were pretty close. Okay. Nowhere close to exact, but still pretty close. See how to do that? Any questions? Any other questions? Did it clear up all the funny business we did? Okay, good deal. Let's see how they do it. The distance between the x-axis and the graph of f is your radius, and that is your f of x. And the f prime of x then is 3x squared. So the surface area is then, and they did everything in one big step here, similar to what y'all did. Your surface area is 2 pi times that radius, and that radius was your f of x, and the f of x was x cubed. They don't show that, but that's what it is. Times 1 plus f prime, which they calculated there, squared, which they don't show you, but that's 9x to the fourth dx. And they, like I said, they're going to be 1 plus, so that plus 1 doesn't matter. Okay, so that winds up being 2 pi times x cubed, that was your r of x, that was your f of x, times the square root of, and they're taking great ends to show this, the square root of 1 plus 3x squared squared. And then they wrote this out too. And here's how they do theirs. If you don't like the way I do it by saying that u equal blah, 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 and stuff like this, they already look into their crystal ball and know what the dx needs to be without telling you how they got it. And they said, if you let this be the u, the du is in this. Well, to make that work, you already had x cubed. They multiplied by 36 here, so you had to divide by 36 here, which is exactly what we did, but just doing it a little different order. So anyway, that gives you a perfect derivative inside, and this will be pi over 18 on the outside, and it's evaluated. Now, they didn't do the u substitution. They used the u substitution to get this, but they didn't use it to get this. They just said that thing is to the 3 halves divided by 3 halves. So they didn't go back to the 1 plus 9x to the fourth. And then they plugged in there and got the same thing we did. Pi 27th times the square root of the cube root, the square root of 10 cubed, which is 1,000, square root of 1,000 minus 1. And then from that, they did their approximation, which came out the same thing. I just didn't want to do a square root of 1,000. Maybe that would have been easier to do, but 10 root 10 was pretty easy, and I could think through that pretty well. All right, any questions? I have a feeling that might be the last slide, and it is. So let's back up, unless there's questions on that, and let's do example 7. Any questions before we launch into 7?
What is the application of surface of revolution?
An application of that? Okay. Let's say you were designing a megaphone for a speaker, okay, and you knew approximately the curve you wanted to have to give the best sound quality going out. How do you tell your manufacturing person what shape to have for that? You know, what surface area, what materials he or she needs to compute that. Something sort of like that. I use that just because that looked like a megaphone and that reminded me of that. But, yeah, something like that. Or anything else you want to make up. It sounds good. Okay. Now, this next one almost looks similar, but it isn't. It's find the area of a surface formed by revolving the graph of f of x equal x squared, not x cubed, on the interval 0 to root 2 Now, unless told otherwise, that's always x, the interval from x, 0 to root 2. Okay? About the y-axis, I can't write, sorry. Okay, about the y-axis, as shown in the figure. So, since they didn't show the figure, shame on them, I will try to draw something similar. Okay, now we're just using the right-hand side, and this is a parabola, and you're going to root 2 here, 0 to root 2, and a parabola, root 2 is just beyond 1, so it's 1.414, so something less than half of the thing. I probably don't have it. But 1, you would be up here at 1, and then this would be something just beyond here. In fact, you'd be at 2, because the square root of 2 squared is 2. All right. So you're going up here to 2. All right. And you're revolving this around the y-axis. Okay. So you'll have a shape that goes, mirrors it over here, okay? And your arc length interval is going to be something like that. What is your radius going to be here? You're going around the y-axis. What's the radius of revolution? Is it what?
2.
Okay, that's
1.
okay. Let me give you a hint. It's 0 down here and it's 2 up here. So what is it anywhere along the curve? Not 2 up here. It's 1 up here. No, it's root 2 up here. The axis, the radius of revolution is root 2 up here. So it's not a big okay. So what is that measure? If you're going from 0 to root 2, what is that measure? 2. Say again? 2. No. These are the values for x. That's your x-axis down here. Okay? Here's your y up here, or we'll call it f of x up here. Okay? So your radius of revolution here is just x, because that's how far you're going. That's what's revolving around the y-axis, x. Okay? So we got that part of it done. What we need to do now is figure out what the now here we have a problem, Houston. Are we doing our arc length interval, which I like to call our ds, are we calculating that based on dx's or based on dy's? Something that argues for the x is the fact that your radius as a function of x is simply x. That's going to be really easy to deal with. If you get that to y's, where y is equal to x squared, then you're going to be dealing with square root of y's, which is okay. In fact, that may even work better, because when you take the derivative and square it, you might wind up better that way. But, at least right now, it's looking like x might be a nice way to go. So if you did a dx here, what is your ds then?
Right there is x.
What's that?
Right there, that coordinate right there is x.
Yeah, this is x down here. Right. Is that what you meant? Yeah. Okay. It's going from wherever you are. This one happened to end right there, you know. That would be your x value. Maybe up here. That'd be a good place to put it. There's your length of that interval is x. Now I'm saying, see, we're not really doing anything with this part in here or this part here. We're just calculating that part. And the question is, do you do your dy's or you do dx? And it's sort of a toss-up. Which way you want to go? Okay, I was afraid he was going to say that. Okay, if you're going to do dy, then you have to get your this this is y is equal to x squared. Okay? And if you're going to do dy's, you got to get this in terms of, so let's do x is equal to y to the 1/2. Because I know that's what I want to do anyway, is integrate that. Now, I didn't do a plus or minus. Any reason why? Yeah, we're in the first quadrant here, so we don't have to do that. We can just do that. Okay, if you... What's that? Okay, but now our radius that we were talking about here, we have to express as y to the 1/2. That may be where it's going to be a pain in the neck or some other body part. So we'll see. Okay? So where would you go from there? We still need to calculate the ds here. If we're using our dy's, which are here, what would that be? Now it's no longer f, let's just call this g of y. X is equal to g of y. So what would we have to do? Take a derivative, okay, and what would that be? G prime, and this is of y, remembering, is what? 1/2 y to the negative 1/2. Is that what you said? Yep. Okay. And then what are we going to do with that? Square it. So when you square that, what do you get? 1/4, 1 over y, or y to the -1, right? And then you do what? Add 1 to it. Okay? All right. Now I'm going to rewrite that slightly. And what's the next thing you're going to do? Take a square root of it. Okay. So I'm going to take this thing and write it as the square root of 1 over 4y plus, instead of writing that as 1, let's write it as 4y over 4y. So you have a least common denominator, right? Right? Okay. So this will be 1 over 2, because the 4 can come out. And what we have here is the square root of 1 plus 4y over y. Are you sure you want to do it this way? Okay. Now, let's drop back and see what we got. S is equal to 2 pi times the integral. Now we're doing dy's now, so you're going from 0 to 2 on this one. That makes it a little simpler, I guess. And what's your radius? Y to the 1/2. So 2 pi y to the 1/2. That gives you the circumference of that increment. And then your ds will be a 1/2. So I'm going to pull this out here. So that takes care of that. And what we have is a square root. Oh, let's not do square roots anymore. Whoa, that's not what I wanted. Undo that. what I'm going to do here is 1 plus 4y to the 1/2 over y to the 1/2. Now the y's to the 1/2 go away, which makes me feel a little bit better. And I guess what I forgot to write is when we do all this, we wind up with a dy. You change from ds to dy when you did that manipulation.
This is 1 plus what?
1 plus 4y to the 1/2 power. Y'all, this is all Dawson's fault, by the way, you know. Okay. So what do we get? It's going to be a pi. That's all we got left out there. How do you want to do this integration? There's a couple ways you could do it, but you tell me how you want to do it. I can't hear. Someone say something. Okay, y'all chose to do a dy. So how do I do the integration? Say again? A du? Is that what you said? Get it to a u substitution? All right, I'm going to do it up here. Then let u equal what? 1 plus 4y. Very good. Okay. Then, what do you do next? du is equal to is equal to 4. Say again? Whoa, whoa, whoa. You're just taking a derivative, not integrating. 4 what? dy, okay? Let me write it that way. Since we have a d on the other side, put a d on this side. Other way to say it is du dy is equal to 4, but let's write it in differential form. Du is equal to 4 dy. Okay? Now, right up here, we don't have a 4 dy, we just have a dy. So let's divide both of these by 4. Okay? So, now we have our pi. There's my integral with limits, but I'm not going to put in the limits yet. And what is 1 plus 4y? What is 1 plus 4y? U, okay. That's u to the what? 1/2 power. And then my dy is 1/4 du. So I'll put my du here and put my 4th out there. Okay? Now, except for my limits, which I think we'll do now, how do we manage those? Goodness gracious, I'm getting a headache. When y is 0, what is your u? 1. And when y is 2, what is your u? Second? 9. Okay. This isn't going to work out too badly, I don't think. So what will this be? Pi fourths. And what is the antiderivative of u to the 1/2? Anybody? Anybody? Help me. A little louder. Second? Okay, u to the 3/2 times 1 over 3/2, which is the same as 2/3. And the 2 will go in the 4 twice, so this will be pi 6 out front. So pi 6 is going to be in the front part. And then we've got u to the 3/2 evaluated from 1 to 9. Okay, so pi 6 out front. And what in the world is 9 to the 3/2 power? I think I've told you before the easy way to do this. Take, huh?
Pi to the what?
I can't hear.
Pi to the what now?
Did you say pi to the what power? I didn't say pi to any power. I said 9 to the 3 halves power. Because that's what you're plugging in for the u, right? 9 to the 3 halves is what? Second? Square root of 9, which is 3 cubed is 27. Okay, so that's a 27 minus 1. All right. Okay. So this will be 26 pi over 6, and I can make that 13 pi over 3. Well, just as an estimate here, pi is just a little bit greater than 3, right? And 3 over 3 would be, pi over 3 would be a little bit greater than 1. 13 times something a little bit greater than 1, maybe something close to 15. Maybe 13.61. 13.61, okay. 13.61. All right, that's what they threw 614, as if they had that many significant digits, okay? That would be approximate. 13/3 pi is an exact answer. 13.614 would be an approximate answer. All right. They did it the other way, the dx's, okay? Pay your money and take your choice. You've already paid your money, so you take your choice. Y'all chose the y way. It worked okay. Either the y way or the highway. Never mind. Okay. If you had done the x's, bless you, then you would have done a dx based on this, which would be pretty easy to do. And that would have given you that. Your x would have been your radius, so 2 pi x would be the first part. And then this would be 2x. Square that would be 4x squared. 1 plus 4x squared. That would have been in your radical then. Plus, 1 plus 4x squared. That would have been in here with a x on the outside. That would have worked out all right too. So I don't know. I think the x's probably would have been just a tad easier, but they both work well. Okay? And they give you the right same answer, so that should warm your heart to the coddles, coddles of your heart, whatever they are. Okay, any questions on that?
Yeah.
Yeah, okay, what?
Let's get pi to the 4 times 2u 3 halves over 3.
This up here?
No, it's below. It's at the u and the u.
Okay, where are you talking about on the board? Up here or down here somewhere?
Okay, go to the right.
Right here? Okay. What I had here was 1/4, 1 over y plus 1, right? So I put those two together and put 1 over 4y, right? That's where that came from. And then rather than writing plus 1, I wrote it as 4y over 4y. That's 1, right? Okay? So then I can combine my numerators over the same denominator, which would have been right here. The square root of 4 in the denominator would have been pulled out of 1/2 there, and that left the square root of y in there, so I just leave that in here. 1 plus 4y. Huh?
The square root of 4 got pulled out.
Yeah, because the denominator here is 4y.
Okay.
The square root of 4y would be 1/2 the square root of y. See, the 4 part, the square root of 1/4 is 1/2. Okay? And that left us y in there, once you factored out the 1/4. It was.
I was talking about I was talking about where it's like below that.
Okay, below this?
Yeah, right there.
Oh, well, let's start back here then. I'm sorry, I thought you were on that one. Okay. So, what we did here, this 1/2 canceled out the 2 here, that just gave us a pi. And we had the interval from 0 to 2, because we're still in dy's here. And we had a square root of y here. See, I wrote right here. Your x was y to the 1/2. Remember, that's your radius. So 2 pi x, that's 2 pi, here's the 2 pi was here, times y to the 1/2. But then I rewrote this as this to the 1/2 over this to the 1/2. Those canceled out. So that gave me this thing, 1 plus 4y to the 1/2, preceded by pi. And so what happened next was that thing up there. This became my u, 1 plus 4y. My du was 4 dy. And then I divided by 4, and that made a, what was a pi here became a pi fourths. Okay? And all we had left in here was a u to the 1/2 du, because we pulled out the 1/4 there. So is this the part you're asking about? Okay. So does that answer your question, how we got to that? Or is it the next step too? Next step. Then we integrated u to the 1/2, which is u to the 3/2 over 3/2, which is 7 times 2/3. And the pi fourths here, the 2 went and the 4 twice, and that gave you pi over 6. So that's where the pi 6 came from. U to the 3/2. We changed we had changed them here. Y'all helped me change that, remember? From 0 to 2. When u is 1 plus 4y. Y is 0, that gave you a 1. Y was 2, that gave you a 9. So that's where those came from. And when you evaluated that, I did it up there from 1 to 9. So pi 6, u to the 3/2 from 1 to 9. And that's where y'all came in. Told me the rest of it, right? Got it? Good. That answer them all? Okay. Good deal. Homework exercise, the last example in 7.4. Any other questions on 7.4? Homework exercises here would be example 5. That should be at Calc Chat. Any of the odds 7 through 19. There's a whole bunch of them there. I'd say either 7 or 9. They're both at Calc Chat. 7's at Calc View. Then any of the odds 11 through 19. They're all at Calc Chat. Then do any of the odds 21 through 29. They're all at Calc Chat. Do 31. That's at Calc Chat. 33 is a length of cable like we did last time. That's at Calc Chat. 35 is a gateway arch, which is sort of a similar thing. So I'd say either 33 or 35. 37 is a sector of a circle. I think you could probably do that too. It should be at Calc Chat. Then either any of the odds 39 to 43, they're all at Calc Chat. 39's at Calc View. 45 or 47, they're both at Calc Chat. 45's at Calc View. 49's at Calc Chat. 51, you can explore doing that one if you'd like. That's an approximation problem. 51 should be at Calc Chat, and 53 should be at Calc Chat. You can think about doing 55 if you'd like. It should be at Calc Chat. 57 and or 59 and or 61 should all be at Calc Chat. And or 63. Then do either 65 or 67. They should both be at Calc Chat. And 69 or 71 should be at Calc Chat. All right, it's about time you get to work, right? So the next section. Any questions? 7.4. Okay. The next section is 7.5, which is, we'll wait for a while, okay. Still Chapter 7, Application of Integration, and 7, slideshow from current slide is Chapter 7, Application of Integration. 7.5 is work, so finally you get to go to work, okay. We'll find the work done by a constant force, which is very easy. And then we'll find it by a variable force, which requires integration. Okay. And by the way, let me just look ahead for a moment here. Yeah, I guess we'll do 7.6. I couldn't remember. Yeah, we do all these, sorry. Okay. Getting crossed up. Okay, work done by a constant force. In general, pretty straightforward definition of work. Work is done by a force when it moves an object. Okay? If I were prying on a rock, which I've done before in my life, trying to move that rock, and I was pushing with all these forces using a cheater bar, a fulcrum, a lever, doing everything I can, sweating and grunting and using lots of force to move that rock, but I didn't move the rock, how much work had I done? Okay? Because work, the physics definition of work, is not how much you sweat or how much you grunt or how much you cry about how much homework you've got or anything like that. It's when a force moves an object. If it doesn't move an object, you've not done any work. You have to have force, you have to have motion. If the force applied to an object is constant, then the definition of work is as follows. Okay? If an object is moved a distance d in the direction of the applied constant force F, force is constant, the distance moved is d, that's a constant, then the work done by the force is defined as W is equal to F times E. Force times the distance. That's why if you don't move it, you haven't done any work. Okay? Force times the distance, that's equal to work. The caveat here is the force and the displacement must be in the same direction. Or exactly opposite directions, one or the other. Then it'd be a negative. Okay? But a force like this and a displacement like this, as in my pushing on the chair here. My force is downward, and the chair is only displacing a little bit that way. But it is displacing. Why is that? Because the component of the force downward here is not doing any work at all. It's only the component of the force in the direction of motion that's doing work. If I do the same force that way, it moves quite a bit more because now the entire force is in the same direction of the displacement, so you have more work being done. The force times this component of force not doing any work at all, unless I was pushing it through the floor, which I'm not. Okay? So it's only this component of the force that's doing work. The component of the force in the direction of the displacement. That's what does work. There are four fundamental types of forces. Why in the world they get into this in a calculus book, I don't know, but it's true. These are what I would say natural forces. My pushing on the chair, that's an applied force, okay? We're not talking about these. These are the natural, fundamental types of forces. Gravitational force, that's what's holding us on the planet. So that's what we have to work against when we jump, okay? I don't do very much work against that, okay? Electromagnetic force, that's the force between two charges, either of opposite or the same charge. If they're opposite charge, that force is attractive. If they're the same charges, that's a repulsive force. Gravitational is always, always, always an attractive force, not a repulsive. Electromagnetic can either be attractive or repulsive. Okay? Then we have what they call the strong nuclear forces and the weak nuclear forces. And that's way beyond the scope of this course and most physics courses to explain those. You have to get into quantum mechanics there, and I can't even remember for sure which is which. But if you think about it, what is the nucleus of an atom made of? What's in the nucleus of an atom? Protons and neutrons, exactly. The electrons are out here flying around. Now, those electrons are held in orbit by the electromagnetic forces because they're negatively charged, and those protons are positively charged. Neutrons have no charge at all, right? So here you have those protons and neutrons are into that nucleus. I mean, that is one dense thing, okay? Nucleus of any atom is incredibly dense. It's just that the atom itself is not dense because it's surrounded with this cloud of electrons that have almost no mass at all, a little bit of mass, but not much. And then space, just empty space in between them and the nucleus. So all the mass, pretty much, to speak of, is in that nucleus. And they're packed in there. Now those neutrons have no charge at all, but those protons are all positive charged. What do positive charges do to each other? Repel like crazy, right? Why don't those nuclei blow apart? Because you have, that's electromagnetic force. These nuclear forces are way stronger than that. Do we understand what they are, how they are? I don't, okay? Maybe some quantum physicists do, but they are incredibly strong forces. And one of them is the one that holds that together, and one of them holds other particles in place. So, I don't know. So, why they put that in there, I don't know. It's true, but those are the naturally occurring. And by the way, electromagnetic forces are stronger than gravitational forces. You say, oh, nah. The Earth is holding the moon in place. It take a lot of charge. But think about this. Have you seen this experiment? If you have hair, that's a big caveat here, okay, and you were to comb your hair, and your hair needs to be fairly clean and dry, and you have low humidity. Doesn't happen too much in the South, but if you did comb your hair with, say, a rubberized brush or a comb, and then had little pieces of paper on the table here, and hold the comb next to it, you're going to pick up those little pieces of paper, right? That's because when you comb your hair, you're knocking electrons off your hair onto the comb, so it becomes negatively charged. The pieces of paper are neutral, and when you hold the comb next to it, the positive charges come toward that and lift up. Guess what? They're overcoming gravity because they go to the comb. So see, those electrostatic forces are stronger than the gravitational forces. Difference is gravitational forces act over long distances, electrostatic forces over very small distances, but it's a stronger force. And then certainly within the nucleus, the strong and weak nuclear forces, they act only within the nucleus. They don't attract things, they don't pull other nuclei, other protons off other things. No, they don't do that. They don't act at a very far distance, but they're very strong forces. Too much so. A force can be thought of, this is real simple, a push or a pull. Okay? Very simple way to think of a force. Okay? Every one of those are forces. If they're electromagnetic forces are repulsive, they're pushing. If they're attractive, they're pulling, and all the others are pulling forces. They're attractive forces. Okay? A force changes the state of rest or the state of motion of the body. That's good old Newton's second law, right? A net force accelerates or changes the state of motion of the body. If it's going at rest and you add a force to it, it moves. If it's moving, you add a force to it in the opposite way, you may stop it, okay? Or if it's moving this way, you push this way, you change its direction. Every one of those is changing the state of motion, state of rest or state of motion, okay? So that's what a force does. For gravitational forces on Earth, it is common to use units of measure corresponding to the weight of an object. And what two units will we use to measure weight? U.S. customary? Say again?
Wait.
What unit? Pounds. I mean, anyone know? Named after Sir Isaac Newton. Yeah, that's what we measure. So, in the grocery store, when you see the scales there, and you weigh out the weight of 4 onions, and it gives either ounces and pounds or kilograms and grams, that's not. Kilograms measures mass. If you're doing the weight, that should have been Newton. No one uses Newton, they use kilograms. So, yeah, kilograms measures mass, Newton measures weight. So the scales in the grocery store, they're correct in their measure, but they're wrong in their units. Okay. Well, whatever. Okay. So here is example 1. Really a tough example. Determine the work done by lifting a 50-pound object 4 feet into the air. 50-pound object sitting on the floor, we'll lift it 4 feet into the air, which is bring it maybe about up here. How much work have I done?
4 feet.
4 feet. 50-pound object, 4 feet. What's 50 pounds a measure of?
Weight.
Or?
Mass.
Okay, pounds.
Or newtons.
Weight is a force. Okay? And feet is a displacement. So, what would be your work done by lifting 50 pounds 4 feet?
200.
Say again?
200.
100? So
200.
200?
Because it's 50 times 4.
Okay, you call that foot pounds. Okay, 200 foot pounds. Exactly right. And that's all. Okay, because your force had to be enough force to lift a 50-pound object, so that would be 50 pounds or more force, and you exerted that over a distance of 4 feet. So that would be 200 foot-pounds. We don't have a special unit for work in the U.S. customary system. We just force times displacement, foot times pounds. Okay? Pounds, feet, or foot pounds. Now, some of you may have, sometime in your past, used a wrench that was graduated in foot pounds. Have you ever used one of those? Yeah. It has a special name called a torque wrench. Ever hear of it? Okay. That's not measuring work. That's measuring torque. But it has exactly the same units. Here's the difference. Work is a force times a displacement in the same direction. Torque is a force perpendicular to your displacement. That's a torque. That's a vector force. It's a twisting force is what you call it. And it's a vector quantity. Work is a scalar quantity. That's a completely different issue. But it has the same units, foot pounds. Just in case you were saying, oh, I have a work wrench. No, it's a torque wrench. As if you would ever say that. Okay. And then I think we've already hit on this. That would be magnitude of the force is the weight of the object. Oh, he came back. Okay. And 50 pounds times 4 feet would be 200 foot-pounds. Okay. So the work done is force times displacement. As long as they're in the same direction, you can do that. 200 foot-pounds. Now, we've already hit on this, so let's move through it quickly. In the U.S. measurement system, work is typically expressed in foot-pounds, or if you're really using small things, you can say inch-pounds or foot-tons. I've never used any one of those. Foot-pounds is always what I've used. In the international system of units, which is SI. Now, where did they get SI? Anyone want to have an idea? Who came up with these? The French. And in French and in many of the Romance languages, you put your noun first and then your adjective after that. So there's a système international or something like that. And that's why it's called SI units. Okay. There's a whole history of why that is the case, but whatever. The basic unit of force is in the Newton, which is the basic unit of force is a Newton as opposed to pound here. just like foot pounds, only they reverse them. But a Newton meter has a special name called a joule. Now, whereas Newton was named after Sir Isaac, so you use a capital N for its unit, a joule is named after James Prescott Joule, so it's a capital J. They write the word Newton and joule with lowercase letters, but the symbols for it, capital N, capital J. Okay? Kind of weird. Seems like they'd capitalize Newton meter or capitalize joule, but they don't. All right. Now, there is another system which physicists tend not to use too much, but it's an older system called centigrade gram second, whereas the SI system used to be called the MKS system, meter, kilogram, second. Okay? If you're doing smaller quantities, they used to use the CGS system, that's centimeter, a hundredth of a meter, gram, which is a thousandth of a kilogram, and second is the same second. And that's if you're measuring very small quantities. So the basic unit of force there would be a dyne. They don't use that too much anymore. It's not an SI unit, but it is that. And what a dyne is a, we'll get to it. Okay. The force required to produce an acceleration of 1 centimeter per second on a mass of 1 gram. That's what a dyne is. In that system, the work is typically expressed in dyne centimeters, which are also called ergs, which really is the spelling of energy when you take out every other letter. E-N-E-R-G-S, ergs. Okay. Now, and they say R joules, you'd have to have some times 10 to the minus 7th or something like that to get it to joules. Now, when my older brother was taking physics at Georgia Tech, he was an industrial management major, so he took what they call cookbook physics, which was regular physics, but it wasn't the engineering physics. And his professor said, here's how can you remember what an erg is. If this is a centimeter, what is this? An erg. Okay. It's a dyne centimeter. Okay. So that's what an erg is, a dyne centimeter. I didn't make that up, okay, but I found it useful. The table below summarizes the units of measure. Why are they spending this much time on it? I don't know. That are commonly used to express work done with several conversion factors. So the U.S.'s customary system of measurement of work is foot-pounds, force is pounds, and why they have periodically these vertical lines that are, I have no idea, they're not in the book, and the measure of distance is feet, so we call those foot-pounds. Say it the other way. The SI unit, which they call this international, the SI unit is a joule for work, Newton is the force, and meter is the distance, so a Newton meter is a joule. Okay? The CGS measurement, the erg is the work, dyne, and why don't you spell it out rather D-Y-N, I've never used that, I usually spell it out, D-Y-N-E, centimeter, dyne centimeter is an erg. Okay. Conversions, foot-pounds, here's the difference, folks. A Newton's a fairly small unit of force, whereas a pound's a fairly hefty one. So it takes 1 foot-pound is about 1.3 joules, 1.4 joules almost. So a foot-pound is a larger unit of work than a joule. Not a lot. They're pretty equivalent. But an erg is a very small one. That's why I said you need a 10 to the 7th in there to get from ergs to joules. Okay? Because if you think about it, to get from meter to centimeter, that's a 10 to the minus 2, and Newton to dyne, well, kilogram to gram is 10 to the minus 3, but this one's squared, so that would be 10 to the minus 3, 10 to the minus 2, 10 to the minus 2, that would be 10 to the minus 7, or 10 to the 7, depending on which way you go. And going a Newton is 10 to the 5th dynes, okay? And that's about, like I said, a pound is bigger than a Newton, so that would be this. Now, why? If a pound is between a quarter and 4 or 5 times bigger than a Newton, why are these so close? Well, because a meter is 3 times that of a foot, a little bit more than 3 times. So they sort of balance out when you get to the work units, but in the force units, a Newton is much smaller than a pound, okay? And a joule is 10 to the 7th thirds. And a pound is about, this is going the other way, like I said, between 4 and 5, 4.4. You don't need to know those, so don't sweat them, but just if you ever need them, there they are. Okay. Goodness gracious. Now let's move to work done by a variable force. How are we doing on time? All right. We got, what, about 15 minutes? Okay. All right. This is where calculus comes into place. That is just multiplication. Okay? When the force, variable force is applied to an object, calculus is needed to determine the work done because the amount of force changes as the object changes in position. Variable force. For instance, the force required to compress a spring increases as the spring is compressed. Okay? If you have a spring here and you push a little bit, you'll compress a little bit. A little bit more, and you'll compress a little bit more. But the amount that you have to compress depends on how much has already been compressed. So if you push it that next increment, you have to push harder because the same increment you did before, you have to push harder. It's a variable force. Or pulling, same thing. Pull the spring a little bit, and it's not hard. But you pull it further, it gets harder and harder. Okay? Now, that's a variable force because the force is dependent on the distance that you're compressing or stretching the spring. Okay? Consider an object that is moved along a straight line from x equal a to x equal b by continuously varying force, f of x. Let delta be a partition, good old partition, that divides the interval a into n subintervals determined this way. A is the same as x of 0, that's less than x of 1, less than x of 2, all the way up to x of n, that's the number of intervals we have. That's equal to your b, just like we've done before. So your delta x of I is x of I minus x of I minus 1, okay? It's the interval between any two of those. For each I, choose a c sub I, since the c of I is in between this x of I and x of I minus 1, something in between. Or it could be on one of the two ends, either one. But it has to be in that interval, okay? Then at that c sub I, which is somewhere in that interval between x of I and x of I minus 1, x of I minus 1, x of I, the force is F of c sub I. And because that F is continuous, you can approximate the work done by moving the object through that ith subinterval by the increment. The amount of work done in moving just that little increment there is that F of c sub I somewhere in that interval times your delta I, delta x of I. So on a small enough scale, you can do force times displacement, okay? Because the scale is real small. That's a very small displacement, okay? As shown in that figure, oh, that makes perfect sense, doesn't it? If you go from here to here, you've got a delta x. Just assume that a constant force, even though this force is not the same as that one, pick some value in the middle and say that's a constant force. Okay. So the total work done of the object moves from x sub a, x equal a to x equal b, and why they did this, I'm not sure. Okay. what this was, your delta W here, and then they plugged in what the delta W was, is L sub C sub I this. So it's the summation I equal 1 to N of L sub C sub I times delta X. Well, then if you let your N go to infinity, so your del, which is your partition, the norm, which is the largest one of those, is going to 0, then this becomes an integral F dx. That's what they're leaning toward. So the limit then is your approximation appears to be better and better as your del, your norm, the magnitude of the norm, the largest delta x that you have in there is going to 0. That means your n is going to infinity. So the work done is in the limit as that goes to 0 of the summation of this. Well, that limit of the summation becomes an integral from a to b alpha of x dx. That's your work done by a variable force. If you know the variable force, how it varies with x, then f of x dx, the integral of that is your work. So there's a definition of work done by a variable force. If an object is moved along a straight line by a continuously varying force, it can't jump up, and go from 7 to 15 without doing something every value in between. Continuously varying force f of x. Then the work done by the force on the object as it goes from A to B is given by, here's your incremental pieces, but as that goes to 0, the norm goes to 0, magnitude of the norm goes to 0, the summation goes to an integral from A to B of f of x dx. Okay. The following 3 laws of physics were developed by Robert Hooke, Hooke's law, Isaac Newton, and Charles Coulomb. If you'll notice there, Robert Hooke was a little bit older than Isaac Newton, 7 years older. They were both British. Hooke was well established before Newton came along. He was fairly young, but Newton came along because he was a little bit older when he started school and stuff, but Newton flew past everybody. Hooke did not take it too well, and Newton didn't really like anyone standing in his way. So the two of them really didn't work well together, Charles Coulomb came after both of them had died, so he didn't have any problem with them. So here's Hooke's law. The force F required to compress a string or stretch a string, either one, within its elastic limits. What in the world do we mean by that? Have you ever taken the string out of a ballpoint pen and played with it for a while? You press on it and it goes back out. You stretch on it and it goes back. As long as it goes back to the original thing, that's within its elastic limit. Elasticity is not how it stretches, it's that it returns to the original shape. So the elastic in a band or something like that, it's not how well it stretches, it's how well it returns to its original shape. But if you've ever played with that spring and stretched it just a bit too far and it doesn't spring back, you've passed the elastic limit. So this works only within the elastic limit. The force required to compress or stretch a spring is proportional to the distance d that the spring is compressed or stretched from its original length. And a proportionality means F is proportional to displacement d. To make that proportionality into an equation, you change the proportionality symbol to equal k, where k is the proportionality constant. And that's also called the spring constant, sometimes called Hooke's constant. Depends on the specific nature of the spring. Anyone ever played with a slinky? Very low spring constant, very small. That coil spring underneath your car, really large spring constant there, It takes a lot of force to Make that go a little ways for it's slinky. It doesn't take much force at all to stretch or compress those. Okay, Newton's law of universal gravitation. So this is variable force on a spring, your elasticity law. This is your gravitational law. The force here is proportional to the product of the two masses divided by the inverse square, divided by the distance between them squared. There's a proportionality constant. It's called the universal gravitational constant. Newton came up with this as well as so many other things. Calculus, three laws of motion, light, I think even maybe photoelectric. It was just amazing what he came up with. Okay, so it's Newton's law of universal gravitation. The force F of attraction between two particles of mass m1 and m2 proportional to the product of the masses, inversely proportional to the square of the distance between them. And that's called an inverse square law. That constant of proportionality is incredibly small, 10 to the minus 10 or something like that. Very, very small. And that's why you can't sell it. If this eraser here and my watch here both have masses, but I don't feel any attraction at all between them because it's a very, very small constant. But if we had something, Jupiter and Mars, huge, okay, enough mass there to have influence. When M1 and M2 are in kilograms, D is in meters, F will be in newtons for a value of G. Here it is. I said 10 to the minus 10, it's 10 to the minus 11. 6.67 times 10 to the minus 11 cubic meters per kilogram second squared. Okay? Weird measure. Okay? G is the universal gravitational constant. Doesn't matter what planet you're on. Okay? Later in physics, you'll go F is equal to mg, where m is one of these masses and the other m is the Earth mass. And you're on the surface of the Earth, so you're at its diameter, its radius squared. So you're everywhere in that. Then this G being fixed here, that tells you what that G times the Earth's mass divided by its radius squared, that gives you what we call the acceleration due to gravity, 9.8 meters per second squared, if you're in SI units. That's a physics problem. Coulomb's law, very similar to Newton's gravitational law, except now the force is proportional to the product of the two charges divided by the distance squared. The distance between them squared, same as before. These were masses before, and now they're charges here. There's your proportionality constant. Now this measures electrostatic forces, and they don't give the Coulomb's constant value. If they did, you would see this K was something 10 to the 8 or 9 or something like that. Pretty big number. Not 10 to the minus 11, 10 to the positive 9, I believe it is. But they're giving it, where Q1 and Q2 are electrostatic units, meaning single electron charge. When D is in centimeters, then F will be in dynes, and K would have a value of 1. But if you did SI units, these would be in coulombs, and that would be meters squared. So you get a very, very large number. And I take it by the motion that we must be getting close to being out of time. So we'll pick up with example 2 next time. Sorry we didn't get more done today, but we'll pick up with example 2 next time. There was on the previous page, by the way, Hooke would be a good paper topic. Hooke's law, Newton's law of universal gravitation, Newton, Coulomb's law, or on the previous page, Emily de Bretuil, she basically translated Newton's Principia is called, from Latin into French, and her translation and commentary greatly contributed to the acceptance of Newtonian science in Europe, which is pretty incredible. not much was done by women back then. She was way ahead of her time. If you'll notice her years composed to Newton, she came along before Newton died, okay? And probably did, well, he had died probably by the time she did the translation, because she would have had to be a bit older. All right, we'll pick up with example 2 next time. Any questions? We'll move along now. That was a lot of blah, blah, blah. We'll move along a lot faster now. Any questions?